Alright, due to some technical issues, I don't have that much storage left on my phone to film this video, and so I wrote out all of the results, and I'm just going to explain them just to make this go fast so that I don't accidentally run out of room, which I have done on past videos. It's not fun to have to go back and redo stuff. Anyways, so we have this proposition: G is nilpotent if and only if there is a subgroup of the center of G such that quotienting by that subgroup is a nilpotent, gives you a nilpotent group. And so for the proof, we just proved the forward direction in the past thing, because we know that quotients of nilpotent groups are nilpotent. That doesn't even use this, that it's contained in the center of G. So for the other direction, we better use this, and we definitely do. Anyways, let pi be projection, and suppose that n is the exponent such that c to the n of g mod a is e. Then let's see, you're projecting c to the n of g. We just proved this in like the last proof or something like that, that you have projection carries through under the c's. So you have the projection of c to the n g is e, and so that means that c to the n of g must be contained in A, because projecting this subgroup lands in E, and so it's contained in the kernel. So this is contained in the kernel of pi, but the kernel of pi, since it's the projection map, is precisely all of A, and thus this is contained in A. However, we know by assumption that A is contained in the center of G, and so this thingy, so C to the n G is contained in the center of G, and so if we look at C to the n plus 1 of G, then this is contained in the commutator of G with C to the NG, but since C to the NG is contained in A, that's contained in the commutator of G in A. And if we look at that, this is generated by elements of the form GA, G inverse A inverse, where G is in G and A is in A. But because A is in the center, we can commute it past G inverse. We can commute elements of A past any elements of G. And so you can put these A's together, and then these G's end up together, and they cancel out, and you get the identity. And so that means that if n is what you need to get the quotient down to the identity, you just need one more. You just need to apply C one more time to get the group. You need to apply C to the group just one more time than that to get down to the identity. And so that proves the other direction. As a result of this, it's not true that if you have a group and, let's see here, there was sort of like an if and only if statement like thing for solvable groups. Let me just remember how exactly that goes. Right, if you have a normal subgroup of a solvable group, then the group is if you have a normal subgroup of a group, then the group is solvable if and only if both the normal subgroup and the quotient are solvable. That is not true in the case of nilpotent groups, because you can look at this example. We have 1 to G1 to G2 to G3 to 1. Here we're stating this in terms of short exact sequences. It's in the same idea. So this is a short exact sequence. The nice thing about working with short exact sequences, we don't have to like start with the normal subgroup and then choose the and then figure out what everything else has to be. We could just take a short exact sequence. But then I guess you have to prove that it's a short exact sequence. Anyways, all the details in this example I'm going to leave for you. If I do end up someday uploading all of the exercises that go along with this class, and I'll upload a proof of all this, or most of this, but I don't think that might not happen. Anyways, so we have a short exact sequence. G1 is just the identity matrix plus you have a complex number up there. G2 is matrices where you've got 0, well, you can read it. And then G3 is just CX by CX, and then this I here, this is inclusion. Obviously anything in G1 is in G2, and phi, you just send A, B, 0, C to A, comma, C. You can prove that that's a group homomorphism, and that's just because of how matrix multiplication works when you've got this 0 here. Okay, and you can prove that G1 and G2 are nilpotent. G1 is obviously nilpotent because if you multiply any two things together, like if you multiply 1x01 and 1y01, you'll get 1x plus y01, and since addition is abelian, this is an abelian group, and so when you take the commutator, you get the identity, and so it's automatically going to be nilpotent, and in fact solvable. Well, wait. Yeah. So just nilpotent. But also solvable. Yeah. But that doesn't matter. And then G1, so that's G1. G3 is, again, abelian, so it's going to be nilpotent. G2 is not. What you can prove is that the commutator of G2 is G1. You could just do that by computation. Like, just take an element in the commutator of G2, prove that it has to be an element of G1, and then you can prove that any element of G1 is attainable using a generator for using an element of the commutator of G2. And so that gives you that. And so what you prove is that the C1 of G2 is G2. C2 of G2 is G1, but then you prove that like C3 of G2 is just G1. Whenever you take the commutator of G1 with G2, you get G1. And so you're stuck at G1 and you never get down to the identity, and thus G2 itself is not nilpotent. So that's that example, and that's sort of neat to know that that thing doesn't extend from solvable groups to nilpotent groups. So that's a little not nice, but we get to some nicer stuff down here. So first of all, p groups are nilpotent, so we're going to induct on the exponent here. If you've got a p group, order p to the r. If r is 1, then g is just z mod pz, and so it's abelian, and so its commutator is trivial. And so it is nilpotent and in fact solvable. But that's not important. If it holds up to r minus 1, so we're doing the induction step, the center of G is non-trivial. We know that. We know that the center of any P group is non-trivial. And so the center of G, it must, and the center of G must have order, which it's a subgroup, so its order must divide the P group. So it's it must be isomorphic to Z mod P to the mz for some m less than or equal to R. And then if m equals R, then the center is a whole group, and so then C2 is just a commutator of an abelian group, which is just trivial. If m is strictly less than R, then what you do is you quotient out by the center, and you just take, let's see here, this is P to the R, this is P to the M. The orders of the quotient, you get P to the R minus M. R minus M here is going to be greater than or equal to 0. But it's R minus M, if M is strictly less than R, then R minus M is going to be strictly less than R. And so you can apply the induction hypothesis here. And so what you get is you get G mod ZG is nilpotent. And then, so we look at here, so ZG is our subgroup A here, because ZG is a subgroup of ZG. And G mod ZG is nilpotent. That's what we prove here. And so applying that previous proposition, we get that G is nilpotent. And that does that. Lastly, you can prove that nilpotent groups are direct products of P groups. There's an exercise that we were given. It was prove that the following are equivalent. If a group is nilpotent, all CLO subgroups of the group are normal, and then the group is a direct product of P groups. And there's some stuff that you can use to prove that, so it's a little tricky. Hopefully I'll upload that at some point. Maybe I won't. We'll see what happens. But if you want to see a proof of that, just Google it, and you can probably find it somewhere, maybe, hopefully. But yeah, there you go. And that finishes this lecture.